be the mass spectrum of this particular molecule. So what types of a signal you will get? I mean, obviously, you will see the molecular ion pair, which is just a radical cation of this molecule. So that is the first thing you will get. The neutral species will not be seen by the mass spectrometers, so it's got to be a radical cation. I mean, it's got to be a cation or the radical cation. For that particular molecular weight is of 100, and then the molecular weight versus charge ratio, typically singly charged species, just 100. So we're going to see the spot and peaks at 100, but the molecular ion peaks are always normally very small. So that's not going to be the base peak. So, the base peak, if you forgot about what it is the highest, most intense peak that probably not going to be the molecular ion peak. Then, probably the fragmentation will produce the base peak, and what fragmentation you will see, what fragments will be responsible to the base peak. So there is many bonds can be cleaved. You can maybe this methyl group can be go out, maybe ethyl go out, propyl goes out, in many ways. But you got to think about what types of ions and the radicals they produce. So I think the first thing we think, to think about is probably the more substituted fragment would be the probably more stable one to produce first. And then if you somehow break this bond there, and then given the cation on that side, you're going to get the secondary carbocation that probably is one of the best things to do for the molecule. They also make the primary radical, because the other side is going to be radical, this side is going to be carbocation. Is that the only secondary carbocation you could use? No, I mean, of course, you're going to first figure out what's the molecular weight, of that particular fragment, that's particularly 43, and that's what the calculates for in case you want to add up the number of the carbons and hydrogens. But this radical, you're not going to see it at all. Because the neutral species, they don't deflect on the magnetic field, so they don't move to the detectors. So they're not going to be observed. There's another way you can create a secondary carbocation and make this methyl, the radical goes out. That will produce a much bigger fragment, and that's just the one methyl group's off. The molecular weight of the methyl group is of 15, so 100 minus 15, that should be 85. Right? So that would be the secondary carbocation, I think it would happen. But it also produced with a methyl radical. There might be other fragments possible, but we are considering the major ones, the big ones. So I'm not going to talk about every single detail, but I think those two will be probably the prime contenders to become a base mix. As I said, the molecular ion peak is going to be small. It will be probably the most highest number, which matches the molecular weight. But because it's not going to be the large, but they're not going to be the base mix. Then out of those two other fragments, which one do you think will be the base pair? The most stable intermediate will make a signal bigger. But if you're looking at this side, that's a secondary carbocation. Then it's also a secondary carbocation. So we're not matching stability on both fragmentations. But what is the difference is the radical stability is different. There's a primary radical, this is a methyl radical. If you're considering the radical stability, the more substituted radicals are still more stable. So because of that, this is the most stable than the others. So, but these things happen together. It's not just radical alone produced. Radical produced with the cation. So we got to think about the stability of the both together. So this stability here will be better than the other because this is secondary carbocation, but radical is primary makes it better than being just methyl radical. So because of that, I believe the base peak is going to be the 143, considering this part, and then 85 peak is going to be smaller. It will happen, but it's going to be smaller. So this type of practice is something that I really want you to do whenever you look at the molecule. If you have a mass spectrum is available, you can simply just cover that and then try to imagine what the spectrum looks like by just going through this process. That would be a good practice for each of you at home. But this was a pretty simple one because just a hydrocarbon. What about this one? Now, I got almost a backbone. I only added the hydroxy groups there. So molecular weight increases because I added the OH groups there. So the molecular weight is going to be 116. that will be the base peak. The base and that will be the molecular ion peak. But hardly this will become a base peak. So what would be the base peak? Then we're going to think about the fragmentation we did earlier. So what you could do, we can probably make a fragmentation based on the degree of substitution like we did before. So let's do the same process. If you break that bond right there, then we're going to create a secondary carbocation, which was the base peak in the previous slide. But will this be the base peak for this molecule as well? That's the question. Right? That's something that you're going to think about. The backbones are exactly the same. I only added the OH there. So it's only minor changes. If you think about it, I only changed like a 15% or 20% of the molecule. So if the majority goes same, then you expect that this will be the base peak for the molecule. But that's the way you can understand why this is happening, what the difference between the examples, and things like that. So another things you gotta know for the alcohol, for instance, dehydration happens pretty quickly. Dehydration is making the water goes out. So that will be the N-18 peak because the water is 18 in the molecular weight. So this will be something like this. The position double bond can be here, can be there. There will be a lot of mixtures there. But assuming this goes out, you have a double bonds right here. That still will be the radical cation because we only kick out the neutral water. So still going to be the radical cation. They can probably go through the one more fragmentations. And that molecular weight is going to be -18, so it's going to be 19. But I don't think that's going to be base peak either, because dehydration happened, even that one might be there or not. This may be showing up. Still, I don't think that is the most stable fragment here yet. So what else can happen with an alcohol? Dehydration is one thing, but there are other things that we talked about at the very end of the last class for the alpha cleavages. What is an alpha cleavage? Oops. It will come back. Somehow it does that. No. Okay, so the other thing is alpha cleavages. So what is alpha cleavages? We have, whenever you got oxygen, nitrogen, or the carbon use a substitute, we are talking about that carbon bearing that things, and the next carbon cleaves. So that's an alpha cleavages. So why alpha cleavage is happening? Because it produces the carbocation next to the oxygen, which has a lone pair. And oxygen will use the lone pair to make it resonance stabilized. So this is a resonance stabilized intermediate carbocation. So you can already imagine that this will be pretty stable. So alpha cleavages make this fragment there, and then that will be kicking out this part. So it's going to get, the 61. So we got several contenders to be at the base peak, and then you got to decide which one we go for. That is what we kind of did in the previous slides without an alcohol as a substituent, but having an alcohol there, that changed the game. So you have to understand why things go different way. And so this molecular ion peak 116, you may be able to see it or maybe not. That depends on the molecule, depends on how you actually get the spectra at the time. It might be absent, even though it is, it's going to be small. The next thing is going to be the dehydration peak. I think that would be the highest of that because dehydration happens pretty quickly. So 98 peaks, but I don't think that's still going to be the base peak. So that one will definitely show up. But I think this alpha cleavage one is going to be the primary base peak because that is just a secondary carbocation. Compared to that, this is the resonance stabilized carbocation. So you can imagine why the fragment by the alpha cleavage is equals the base peak here. The question still raised there, is that the only one you're going to see for the spectrum here? Is that the only alpha cleavages it can make? And you should imagine that there's another bond that can be cleaved. I mean, this carbon and carbon is bonded, that cleaves. That is also alpha cleavages too. So there may be the multiple fragment happens by alpha cleavages because these carbon have a two carbon substituents. If that one breaks, cation is going to be given this side, then you're going to have this fragment shows up. And that is also the resonance stabilized. So this is still the stable, secondary carbocation. So that is still the alpha cleavages. And that one, the molecular mass versus ion ratio is at 87. I think this one is going to be almost as close to that one. This make the ethyl radical goes out. That's still the primary radical. So I cannot compare which one's going to be more stable. They're still, both of them are primary radical. So there should be probably very similar height for this one, for that one, and this one. So I'll kind of put it there almost equal height for that one because I cannot figure out which one's going to be bigger, but both are products of alpha cleavages. So I'm going to tell you that alpha cleavages actually makes a significant stable, fragment.
Get to like ish, like
87? To me, to my knowledge, I wouldn't be able to tell the differences. You may actually measure it and then you'll see the differences. But before that, I wouldn't know. I mean, I would expect a similar stability for both parts. So I would expect they were about the same. Yeah.
So both of these are alpha cleavages and that one was dehydration. What was the very first unit?
This one?
Yeah.
That was just breaking out that thing.
But they're
Timing that's a secondary carbocation.
that's different.
Yeah, like what you see before the previous slide. But I don't think for the previous molecule, that was a base peak, but not this molecule because of the hydroxyl groups there. Yeah. I just want to point out that it depends on what molecule you're dealing with, potential changes. All right, so would that be the only big peak you're going to see? I just want to point out that there might be one more. May not be the base peak, but there is a silver one more, which is that dehydration peak. That one, you got the double from there. So if that method goes out, you're going to get the resonance stabilized and really carbocations. I mean, of course, this may not be as stable as the other because it's going to be processed from the fragment. Fragment becomes another fragment. So chance is going to be a little low, but I think that's still going to be big enough because then the fully repeats because we still have a stability there. So that one, I kind of maybe too big. I might just bring it down to maybe that much. I don't know. I'm only estimating, but you got to figure out what fragments will be produced. But when instead make the fragmentation, they don't normally make another fragment which can add the fragmentations unless it's a neutral when it will kick out like the dehydration peaks. But at least you got to anticipate what's going to happen to the molecule if the process is given. So those are something that I really want you to practice to get to know the molecular mass spectrum meters and then their related process.